Thank you. I am so happy and honored to be here. And thank you again to our wonderful hosts and everybody who puts on this event every month. So let's thank them again. It was just great to be here. And I can't believe I have to follow Jeremy. He gives such great talks. And I knew when he was going first, I'm like, oh boy, I've got a lot to live up to. But that was a really wonderful introduction to Chandra and X-ray astronomy. And I have the fun and impossible task of hitting on some of Chandra's science highlights from the past 20 years. And this is really impossible because Chandra has contributed so much to so many areas of astronomy. And I'm going to try to show you some examples from different distances, different size scales, and just give you a sense of the breadth of what Chandra has done in terms of groundbreaking transformational research. My history with Chandra began when I was an early graduate student, and I actually got some of the very first Chandra guest observer data in 1999, and it formed part of my thesis. And I've been a high-energy X-ray astronomer, observational astronomer ever since. And I am familiar with a lot of this science, but not all of it is mine. So I will do my best. Yeah. A little closer to my mouth. Sorry. Okay. I will do my best to answer questions, but again, I'm not an expert in all of this. So Jeremy talked about the first light image of Chandra, where you saw those excited people in the control room, Martin Weisskopf pointing at the screen. Now, the public release of Chandra's first light images, they released two things. One was a point source to show how good the focusing capabilities of Chandra were. And the other first light image that was released, which is the one that always sticks in my memory, is what I'm showing here. At least I'm showing a portion of it right now. And the reason I'm showing just a portion of it, because I'm zooming in on the very central regions of this first light image. And when astronomers across the world saw this, I know they were all excited, because seeing this in the center of this object, and I'll explain what it is, was such a confirmation of everything we thought we knew about stellar evolution and death. So this is an image of a supernova remnant that exploded about over 300 years ago. It's a supernova remnant called Cassiopeia A. And this thing in the middle is a neutron star. It was a compact object left over after the supernova explosion. And this is what we had always thought was supposed to happen. Stars more than about 8 times the mass of the sun, when they explode, when they end their lives in this violent explosion, they leave behind a neutron star or a black hole. And to see that point source left behind by the explosion was such a wonderful confirmation of everything we thought we knew about stellar evolution. So let me zoom out. And as wonderful and impressive as this is, I think the full image is even more impressive. Let's see, there we go. So this is the full first light image, one of the two that was released by Chandra. You can see not just that central compact object left behind by the explosion, but this amazingly complex, complicated interaction of the ejecta that was thrown off by the exploding star interacting with the material surrounding it, just giving us this amazingly detailed picture of that complicated interaction. So this X-ray image is what's called an intensity image. The brighter portions have more X-ray photons than the dimmer portions. You can think of this kind of like a black and white image. All of the colors that we show in X-ray images are completely arbitrary, as Jeremy said. So this is like a black and white image. The brighter areas just have more counts, and the dimmer areas don't. But the amazing thing about Chandra, and this is in contrast to a lot of other areas of astronomy, like optical astronomy, is Chandra can record what the energy of every single photon that it records is. The way I like to explain this to my students is there's this famous story about Ray Charles when he was starting off, that he insisted on being paid in $1 bills because he could count all of them, and then he would know how much money he had. If somebody told him they were giving him a $20 bill, there was no way for him to know. So he insisted on having 20 bills so he could count them out. So imagine that you're blind, or I blindfold you, and I give you a stack of money, and I ask you a stack of bills, and I ask you, how much money do I have? I mean, you could count the bills, but you don't know if you're counting ones or fives or tens or 20s or hundreds. And that's the way a lot of branches of astronomy operate. They don't know exactly what the energy of the photon is. So they can filter it, they can restrict the energies that get to the detector, but they don't know the exact energy of the detector. So they never know exactly how much money, how much energy they've collected. But that's not true with Chandra. With Chandra, we know the denomination of every single photon. We know the energy of every single photon. And so we can make images that actually have that information encoded. And so now we're going to revisit this. But now the colors here are representing the different photon energies. Higher photon energies, higher X-rays are in blue, and lower energy X-rays are in red. And now let me zoom out from the central regions to the full remnant. And what you see here is this amazing picture, not just of the complicated interaction, but of the different photon energies and where they are in this element. And one thing that we understand from basic physics is that different photon energies can correspond to the emission lines of different elements. So there are some photon energies that must have come from a particular element and only that element. So we can translate this map of photon energies into a map of elements. And that's what I'm going to show here. So here's the remnant, and here's the remnant now in different elements, in silicon, in sulfur, in calcium, in iron, and then in emission that's associated just with the interaction of hot gases interacting with each other, and that blast wave. And this is just absolutely phenomenal. Because again, this is a wonderful confirmation of the story that we have built up, that we understand about stellar evolution, which is that these massive stars, throughout their lives, they build up these heavy elements through nuclear fusion in their cores, and when they explode, they disperse those elements into the universe. And that's what you're seeing here. You're seeing all these different elements that we are familiar with here on Earth being cast out into space by the supernova explosion. And this is to the point of what Carl Sagan once famously said, that we are all stardust. Remember, what makes us up, and we've been able to do this in astronomy, is to map out the different elements in the periodic table into how they're formed in the universe. When the universe started, it was just hydrogen and a little bit of helium. And through stars, through stellar explosion and stellar nucleosynthesis and collisions of neutron stars, we've built up all of the rest of the elements, starting out from just hydrogen and helium. And we know how each of these different elements was made. And all of the ones in orange were from those exploding massive stars, like I just showed you, which is the majority of the stuff that makes up our body, the oxygen, the carbon, the silicon, I mean, the stuff that makes up the Earth as well. So this was, again, just a beautiful and amazingly beautiful picture of this process. I'm going to talk a little bit more about a couple other supernova remnants, some that Jeremy also mentioned, just because that's one of the most striking examples of the power of Chandra, which is its exquisite spatial resolution to show us these fine details, and also that energy resolution to know the energy of every incoming photon. Okay, so Jeremy talked a little bit about this region of the sky, this Tycho supernova remnant, so I won't go through the whole history of it. This is it in optical light, and this is what it looks like in X-rays. And Jeremy gave you some sense of that, how that expansion took place. And there's actually been not just those two images that were shown previously, but there have been a series of images of the supernova remnant that were taken over the years. And so I'm going to show a time lapse of those images where you can see that remnant expanding in real time. I mean, it's just an amazing thing to think that, you know, on the scale of just a few years, we can see such large-scale changes from this explosion that happened, or that was first detected 300 or so years, or 450 years ago for Tycho. And just to zoom in a little bit more to the outer regions of it to show you how that's happening, I mean, it's absolutely amazing to see this level of detail in an astronomer's lifetime. And that's only possible because of Chandra's amazing spatial resolution, that we can resolve these very thin, very faint structures and see how they move over the course of just a few years. Okay, so the next remnant that I want to talk about is another one that Jeremy introduced, which is the Crab Nebula. And I want to show it to you in different portions of the electromagnetic spectrum. So in optical light, taken with the Hubble Space Telescope, we see this wonderful filamentary structure, kind of reminiscent of what we saw in some of the other remnants, where the outflowing ejecta interacting with material, causing these this really detailed, complex structure. In the infrared, we see this sort of diffuse purplish glow. And again, these are false colors. This is somewhat arbitrary how this was colored. And then with Chandra in X-rays, we see this much smaller structure shown here in the blue light. And when we put them all together, we see how they fit together in this image down here. And I will go ahead and zoom in on that. So this is about 10 light years across. And you can see how that X-ray nebula is contained within that infrared and then the optical nebula on the outside. And what we understand now is that this pulsar at the heart of the Crab Nebula, that bright X-ray spot in the middle, this is a neutron star, amazingly dense, compact object, about 1.5 times the mass of the sun and about the size of a small city, spinning around once every 33 milliseconds, if I remember correctly. And it's unleashing a torrent of matter, antimatter particles into the surrounding nebula and actually powering the nebula. Why is this so bright in infrared and optical light hundreds of years after the explosion? It's because it's being powered by that pulsar. And the next thing that I want to show you is a close-up of the central regions of that pulsar, and in particular this inner ring right here, which is thought to be that location where these particles are coming out and interacting with the surrounding nebula and depositing their power, which is eventually making its way outward. And this is going to be another time lapse, and I want you to see and get a sense of how the energy is actually flowing outward from that pulsar. You can see that ring moving outward and just get a sense of the energetics of how that central pulsar is powering this entire enormous nebula that's 10 light years across, when the thing itself, again, is only the size of a small city. But it has a huge amount of rotational energy that's being dumped into powering this pulsar. Okay, so supernova remnants are, again, one of the most beautiful examples of Chandra's power in both spatial resolution and spectral resolution. But I want to move on to talk about some other objects. The first thing I'll talk about is another type of object located in our galaxy that we've studied in detail, and these are globular clusters. Shown here is one called 47 Tuc. It's one of the most famous ones. It's in the southern hemisphere, so you would never see it from your backyard with a telescope. But it's a collection of about 100,000 to 1 million stars in a pretty small region of space. It's kind of like a little mini galaxy. And we have about 200 of these in our galaxy. And this is what it looks like in optical light when you see all of the different kinds of stars, 100,000 or so of them. And when we look in X-rays with Chandra, we see several dozen, maybe 100 or 200 or so sources in this globular cluster. And this is not only showcasing Chandra's amazing spatial resolution, but this also solved a decades-long mystery in understanding globular clusters. Like stars, globular clusters would have collapsed long ago if they didn't have some internal energy source. Globular clusters are among the oldest structures in our galaxy. They're 13 billion years old. And long ago, they should have collapsed and dissociated, much like a star would when it runs out of energy. And what was thought could provide that energy for these clusters were really tight binaries, were really close binaries, stars orbiting each other. And the cluster has a way of actually tapping into the orbital energy of the binaries as an internal energy source. So this was an idea. The problem was, for decades, optical astronomers looked for binaries in globular clusters and didn't find any for decades. And this was a really big problem in the 90s. And then Chandra comes along. And the amazing thing about this image is every single X-ray source that you see there is a close binary, or the offspring of a close binary. So immediately Chandra picks out the several dozen most interesting and important sources in this cluster and resolve this long-standing mystery in understanding these structures, these globular clusters. The other reason why I love this image is this, studying globular clusters, which is something that I do in my research, is another amazing example of the power of technological progress in astronomy. That's going backwards. Let me go forwards. Here we go. So here are 3 images of that same globular cluster, 47 Tuc. This first image on the left was taken with the first imaging X-ray satellite, the Einstein Observatory, in 1979. And you see something, sure, but you only see that one thing. With a slightly more sensitive and slightly better telescope in the 90s, the ROSAT telescope that the Germans launched, you can see that there's definitely probably more than one thing there. But this is an image of the exact same portion of the sky taken with Chandra. And I think the images speak for themselves. When you have the spatial resolution and the sensitivity, you uncover a world that was otherwise completely unknown. And as amazing as it is to go from maybe a few sources to, several dozen sources, what's even more impressive is when you go from 0 sources in this other globular cluster. This was the ROSAT image of another globular cluster that I study where there was nothing detected there. And then with Chandra, we've detected over 100 sources. And I mean, that's just transformational in your understanding of these objects when you go from nothing to 100 or more sources. And that's the power of that spatial resolution. That's the power of those mirrors that Jeremy talked about. Okay, so now I'm going to move out from our galaxy and show you some Chandra images of some nearby galaxies and how important these have been. So this is an image that I think Jeremy also showed. This is the Whirlpool Galaxy. This is what it looks like in optical light. This is everybody's familiar traditional image of a galaxy that they probably have in their heads, a nice spiral galaxy. This one has a companion up here. When we look very deeply in X-rays, and this image was, I think, over 1 million seconds of Chandra time, we see not only a number of point sources, those bright spots in this Chandra image, but also this purple stuff is a large-scale diffuse hot gas. And all of those point sources are neutron stars and black holes that were formed in supernova explosions that are accreting material from a companion object now. They're the kinds of black holes and neutron stars, we understand how they form, that were formed in an explosion like that first image that I showed. And we put them together and we show these nice composites to try to get a more full and complete picture of that galaxy and understand where that hot X-ray gas is, where those compact objects are. And it's data like this that lets us understand and get a much more complete picture of galaxy formation and evolution and these important processes of feedback that regulate some processes that we still don't fully understand and that we won't unless we really look at them across the electromagnetic spectrum to get the full picture. So this is a beautiful image of the Whirlpool Galaxy. I'll just show another one. I'm not going to talk too much about this one. This is M81. It's a similar type of composite where you have X-rays in blue, optical in green, infrared in that pinkish color there, and ultraviolet in purple. And they're all put together in this beautiful image of M81. What was important about this data is we know now that most galaxies have a central supermassive black hole. So this is unlike the ones that are formed in supernova explosions. These supermassive black holes at the center are like 1 million to 1 billion times the mass of the sun. But they're a black hole. And this data set showed us that these supermassive black holes, they accrete material, they feed in much the same way that the smaller stellar mass black holes do, these other points of light. And so this was a nice confirmation of Einstein's theory of relativity and the theory of black holes, that these things should just scale with mass, that they're all really the same type of object, just one is 1 million times heavier, 1 million times more massive than the other one. But that they all basically follow the same rules for how they accrete material. Okay, so now I'm going to move out from galaxies to an even larger scale, which is clusters of galaxies, which are the largest bound structures in the universe. Clusters of galaxies are the largest known structures in the universe. And I'm showing here an X-ray only image. And what you're seeing here is what you might not expect to see from a cluster of galaxies. You might expect to see a bunch of actual individual galaxies. And that's what you would see in optical light. You would see little white blobs everywhere that were these galaxies, these collections of stars. The scale here for the people that can't see the bottom line, this is 1.3 million light years across this image. This is a truly enormous scale, spatial scale. And what's shown in X-rays is this extremely hot emitting gas that is contained within this cluster. So there's this deep potential well, and you have these individual galaxies like the Milky Way, but you also have this huge reservoir of gas. And this gas actually makes up the majority of the visible matter of the cluster. There's more matter in the X-ray gas than there are in the stars and the individual galaxies. So what's amazing in this gas is not just how much there is, the extent of it, but the amazing structure in it. You can see all of these bumps and wiggles. And what you're seeing here are actually pressure perturbations, basically sound waves in this gas, but on an amazing scale. And these sound waves are showing us how energy and momentum are transported throughout this huge cluster. That a lot of the driving action is done from the central supermassive black hole of one of the galaxies that's at the heart of this cluster. And it's sending out a lot of pressure, a lot of momentum, a lot of energy, and it's keeping this cluster gas at extremely high temperatures so that it emits in X-rays. And this was a big problem to understand. How is this gas hot for so long? And it's because it's getting heated by this deposition of energy that is being carried by these pressure waves. One thing particularly of note is this large structure, if you can see it down in the bottom portion here. There's this huge arc down here. This is about twice the size of the Milky Way galaxy, and it's basically one huge wave. It's a wave not unlike what happens when you have air going across water on the in the ocean. When you have wind blowing across the water and you create waves like that. What likely created this huge wave here is a smaller cluster kind of grazing the outskirts of this larger cluster. And when you have fluids of two different velocities pass each other, you create waves like that. That's how you create waves on water from air. And it's the same type of process happening here. But again, this is twice the size of our entire galaxy. So it's pretty amazing. And just to zoom in on the central regions of that to show you how detailed this structure is, I just wanted to show this because again, it just amazes me as an X-ray astronomer that we have such exquisitely detailed pictures of things happening on this scale. So I'll talk about another cluster of galaxies. One of the most important clusters that Chandra has observed, one of the most important clusters in astronomy. It's called the Bullet Cluster. Here is a picture in optical light. And it's actually, we call it the Bullet Cluster, but it's two clusters of galaxies. There's one cluster here. You can see this group of galaxies here. You can kind of see a higher concentration of galaxies there. And there's a higher concentration of galaxies there. And what's happened is these two clusters have actually collided with each other and run through each other. And you might believe that based on the optical image, but you'll certainly believe it based on the X-ray image, which I'm bringing in now. So this red here, this is the X-ray emission. So this is the hot gas. You see these two clumps. Again, each of these clusters had their own reservoir of hot gas that they held with it. They collided with each other. They ran through each other. And what happens is the optical galaxies, the actual galaxies, the things made of stars, you can imagine standing on opposite sides of this room and like you have a handful of BBs and I have a handful of BBs over there and we throw them at each other. Most of those BBs are just going to miss each other and just go right past each other. But if we were holding like leaf blowers at each other and that wind, that gas was running into each other, we would have a lot of interaction there. And that gas would interact. There'd be a lot of complicated hydrodynamics involved in that. And it would get across the room much slower than those BBs would. And that's what we see here. Those galaxies have actually made it past each other relatively unscathed, but that gas from the two clusters has interacted with each other. So the next thing I'm going to show is where we think most of the mass is in this cluster of galaxies. And it's through an analysis I don't have time to fully explain, but basically by looking at the different galaxies in the optical and seeing how they're slightly distorted, it's called gravitational lensing. And we understand how that works, and we understand how that scales with the amount of mass. It's basically telling us the amount of gravity that's there. And when we do this analysis, we can tell where most of the gravity, most of the mass is in this region of the sky. And that's what I'm going to show next. And that's shown in the blue. So this blue here is telling us where the gravity is strongest, where the matter is the strongest. And the amount of matter implied is way more than is contained in all of those galaxies. So this is dark matter. And this is, in fact, this complete picture here is one of the most compelling silver bullet, nail in the coffin proofs of dark matter that there is. You know, most astronomers are convinced of the reality of dark matter, but there are a lot of people who hold out alternative theories of gravity that say, well, you could explain most of the effects that are attributed to dark matter with a slightly different theory of gravity. But when you put the X-ray together with the gravitational lensing mass, and you see where the luminous matter is, where the X-ray gas is, and where the dark matter is, there's no alternative theory of gravity that can account for this. This is the most ironclad evidence for dark matter that we have today. That you really cannot refute this with some alternative theory of gravity. So it's an extremely important image for all of astronomy. Okay, the next thing that I want to talk about, oh, and this is just with the X-ray and the lensing, the dark matter gas. The last thing that I want to talk about is one of the deepest images of the sky, I think the deepest image of the sky ever taken in X-rays. The Chandra Observatory stared at a patch of the sky, a blank, in big air quotes, patch of the sky, for the sum total of about 81 days. Now this has been spread over the entire course of the mission. But this is basically 81 days of observing a blank, big air quotes, patch of sky looks like. And in every image that you take, there's always the light that you have from point sources, and then there's the light that you have that's just kind of background light. That most people, it's a nuisance, you need to account for the background. And we've always known that there's this uniform, nearly uniform, diffuse X-ray background that's just part of every data set. Except when you stare at it for 81 days, you resolve that background into individual sources. And every source, every dot that you see here is a supermassive black hole, accreting material in a distant galaxy. It's at the center of its host galaxy, accreting material. This was confirmation. This was further proof. This was part of the reason why Riccardo Giacconi won the Nobel Prize. This showed everybody the ubiquity of black holes in the universe. That almost every galaxy has one of these supermassive black holes at the center, and that they're pervasive throughout the universe. And the way that Chandra works, it's actually most sensitive in the center of its field of view and a little bit less sensitive toward the outskirts. So if we zoom into the very center in this image, what I show here, this right here in this very small patch of sky, this is the highest concentration of black holes ever seen. And this should be representative of the entire universe. And this is the equivalent of if you looked at a patch of sky that was the size of the full moon, you would have about 5,000 supermassive black holes in that area. And there's nothing special about this area. This is true of every patch of sky that's the size of the full moon. It has 5,000 supermassive black holes in that area. I mean, most of them are very different at the far reaches of the universe, but that's how many there are looking out as far as we can look. And this is one of the greatest contributions that Chandra has made. So I've tried to take you, from where Jeremy left off with things in our solar system to things in our galaxy, show you other galaxies, clusters of galaxies, and now ending at the far edges of the universe. So thank you very much. And I'll take any questions.
So Jeremy said you were going to do the rest of the universe, and I think you actually did. Like all of the universe. So Chandra does all of the things.
Pretty much.
That's impressive. All right, so as promised, we are prioritizing our social media questions. So on Twitter, we got a question from the Earthbound Astronomer. In researching the elemental breakdowns of supernovae remnants via Chandra, do we see common trends across all supernovae with regards to elements or the compositional percentages?
Oh, that's a great question. And no, we do not. We've actually seen very different elemental abundances from the two main types of supernova explosions that we know about. So there are the supernova explosions from a massive star that has run out of fuel. That was the first image that I showed of Cas A. And then there are the other types of supernova explosions, which are from the complete obliteration of a white dwarf. And that would be like the Tycho supernova remnant. And they have very different abundances. They're very different amounts of elements that we see.
All right, so any other questions from the audience? Right here?
Okay, so the question was when Chandra dies, which hopefully is not in 10 years. Chandra was built with no expendable resources. There's no gas. There's nothing like that. It can fly for as long as it's going to be funded. Right now, we're in the midst of what's called a decadal review of astronomy and astrophysics. Yes, the astronomers in the room are like, yes, I've written white papers for that. For this, NASA has asked for studies of 4 large flagship type missions to see which one is viable, which one could do the most science. And actually, the T-shirt that I'm wearing right now is because I'm on one of the science and technology definition teams, and it's for the next generation Chandra. We call it the Lynx X-ray Observatory. That's why there's this awesome kitty cat on here.
I mean, vote for that for the shirt alone. Like,
yeah,
that's
I know,
a lynx
right?
in a galaxy, if you can't tell.
This actually is the Whirlpool Galaxy from Chandra with the giant space lynx on it.
Complete with giant cat.
So we don't know for sure because there's going to be a review process to see. But one of the flagship missions under consideration is a next generation Chandra. And I could talk during the break about the amazing things that could do.
All right. Any questions up top? It's like almost impossible to see up there past the lights. Okay, right here in the middle.
Oh, so Chandra, so it's an interesting thing. If you know anything about the Hubble Space Telescope, you might know that the Hubble just like goes to an object and it sits and it stares at that object and it just stays in the same position because it's collecting photons and needs to collect enough. The way that Chandra works, because it detects each individual photon and knows everything about it, Chandra doesn't sit and stare. Actually, Chandra's kind of always moving around in this sort of Lissajous pattern, this weird sort of figure 8 pattern. And it's because X-rays are very energetic and they don't want to dose any part of the detector too much. But it has phenomenal star trackers on it. So even though it's moving around, it knows exactly where it's pointing. And it basically just reconstructs that image because it knows where on the sky all of those photons came from.
Sounds like magic to me. All right, over here on the left. That was my question.
So how does the detector know the energy of the X-ray photon? So you have probably a phone with a camera on it or maybe a digital camera, right? And the technology of that, I think now they're active sensors. They used to all be CCDs, which is what Chandra has, are CCDs. They're semiconductor devices, and essentially they work by incoming photons deposit energy. And that energy liberates electrons. And those electrons are eventually read out. And you know how much energy you've liberated by the number of electrons that get that get freed from the semiconductor. So that's how much energy got deposited. Now, an optical photon on its own can't liberate electrons. You need a lot of optical photons to do that. But an X-ray photon, which is thousands of times more energetic, a single X-ray photon can liberate several electrons. And so you basically just count how many electrons you've liberated, and that is related to the energy of the incoming photon. It's a very coarse spectroscopy. One thing that hasn't been brought up, Chandra also has a set of gratings. It actually has 2 sets of gratings, which do disperse the light. And that's where you know the wavelength, you know the energy of your photon based on how much it's deflected from a grating instrument. And again, I can't get too far into that. So Chandra also does have that ability to get very high resolution spectra that way, but then you don't have as much of an imaging quality. You lose a lot of photons to that dispersion.
All right, let's thank our speaker one more time.